let's look at this schedule real quickly, just to give you an idea of where we're going. And well, let's see. Someone pointed out to me there may be a error here. Major error right here. All right. The final exam is Thursday, but I think this is July 27th. Is that right? Okay. Change that to a 27th right now, so nobody gets confused. If that's the only error on there, I don't want any errors, but I hope there aren't any others.
So on exam 2 and 3, we'll be doing chapter 6.
Oh, yeah, that's the other error. Let's see. Chapters, this says the first exam says chapters 1, 2, and 3. Come on, move. It says chapters 1, 2, and 3, 4, 5, and 6. Yeah, I think exam 3 would be chapters 7 and 8. I believe. Yeah, 7, 8, and 9. 7, 8, and 9. And that is the last day of class. And then after that exam, we would review for the final. But this prepares you for chapters 7, 8, and 9. So then really what we need to talk about is chapters 1 through 6 again. See what final answers or final questions there are, etc. And then you have Wednesday, all day Tuesday and Wednesday to prepare that for the final on Thursday. Okay? That makes sense? Okay, let's kind of just look quickly at what's in those chapters. Chapter 1 is just kind of some fundamentals about numbers. How do we work with numbers? How do we round numbers off? What do we mean by a significant figure? When is a number significant, meaningful? When does the number have meaning, have some significance, and where does that significance end? So we'll talk a little bit about that. So this is all numbers. Dimensional analysis has to do with looking at the units on a number. You know, if you say, how tall are you? I'm 6 foot 2 inches. Okay, 6'2". That feet and inches. Those numbers have units. You weigh 150 pounds, or you weigh, I don't know what that would be in kilograms, but probably something around 68 kilograms. Those numbers have units, and those units are as important as the number. As a matter of fact, in dimensional analysis, you will analyze the units in a calculation before you even worry about what the answer is in a number, the numerical answer is. And that's stressed in nursing because they stress this for drug calculations, for dosage, determining dosage for a patient. So they stress dimensional analysis. That's chapter 1. Chapter 2, the structure of the atom. So what does an atom look like? How do we know that it looks like that? And then get into the periodic table right there. Trends in the periodic table. Chapter 3, a key part of this is going to be compounds. And how do you name compounds? How do you write formulas for a compound? The salt in your salt shaker, a chemist refers to it as NaCl. What is that? Sodium chloride. That's the formula for the salt in the salt shaker. It's sodium chloride. And there's one sodium and one chloride. That's the ratio of sodium and chlorine in the salt shaker. And that's really critical. So we need to understand how to write these formulas and how to know that, for example, magnesium chloride is not MgCl, it's MgCl2. There's 2 chlorines for every 1 magnesium. Not only will you learn what aluminum chloride. It's AlCl3. Aluminum chloride. Sounds like sodium chloride. Yes, it does, but it has got a different formula. And you need to, so if you're given the name aluminum chloride, you need to transfer it into the right formula, chemical formula. We learned that in chapter 3. That'll be a real critical part of chapter 3. And then there'll be an exam over that. Chapter 4 is the heart of this course. We'll get into moles. What is a mole? It's a very, very big number. Molecular weight, molecular weight. We got the mole in there. Mole is abbreviation of not that little animal, furry animal, but abbreviation for molecule. Molecules. What is the mole? Avogadro's number. Chemical equation, balancing chemical equations, calculations based on the chemical equation. July 4th is a Tuesday. We won't have class that day. Thursday we'll come back. So we'll spend the most time of any chapter on chapter 4. And it has got a lot of math, or you need to really know how to follow the numbers and to get correct answers. Chapter 5, gases, ideal gas law, Boyle's law, Charles' law. These are gas laws. How do gases behave? Why do we even care? We'll learn in chapter 5. Chapter 6, properties of solutions. All right, you dissolve sodium chloride in water and you get a solution of sodium chloride. This is a white crystal in your salt shaker. It's a clear white, water white, looks like water solution, but it now has a certain amount of sodium in it, and we will learn in chapter 6 how to represent the concentration in either molarity or well, let's put here weight volume percent. Those will be the two. This is what's used in hospitals clinically a lot, is weight volume percent concentrations. This is the chemist's preferred concentration of a solution, molarity. Then chapter 7 we get into energy. Energy, rates of reactions, equilibrium. Chapter 8, acids and bases, pH. What is pH? What's the pH scale? 1 through 14. So we'll get into that. And oxidation and reduction reactions. And then, like I said, 8 or so pages of chapter 9. You go into any hospital, and radiology is this way. Okay, every hospital has a radiological department. Why? They're using sometimes radioactive isomers. They're doing X-rays and things like that, but sometimes they're administering iodine, radioactive iodine, to treat the thyroid. So this gives you a little introduction into radioactivity. What is it? And half-life and things like that. All right? So that's what we're going to cover in 8 weeks. So from there, let's start. All right, so chapter 1. Okay, chapter 1. And I'll fly through some of this. You can read it as well as I can explain it to you. Just a little bit of the introduction to chemistry. The highlights here will be, like I mentioned, these are the highlights of chapter 1 that you need to measurement. So we'll look at metric to English conversions, English to metric, metric to metric conversions. How do you convert 150 pounds to kilograms? How do you convert 6 foot to how many centimeters is that? Or meters? How do you round numbers, significant figures, scientific notation, temperature, and density? So the three types of problems here. You may know the mass and the volume, and you need to calculate the density. You may know the density and the volume, and you need to calculate the mass. Okay. There's one other thing we got to do. Let's just pause for a second. What is chemistry? Study of matter, study of chemical and physical properties. We'll distinguish between those two. Water boils at 100 degrees centigrade. That is a physical property of water. I can take a little sample of water, go over and boil it, put a thermometer in it, and see it's boiling at 100 degrees centigrade. It has nothing to do with any other substance, just water. Chemical properties, I could take sodium and throw it into that water, and I see a reaction occur. The sodium is reacting with the water, and it's forming sodium hydroxide. That is a chemical property of water. It will react with sodium. It will react with potassium, rubidium. That's a chemical property. It's describing water's properties in relationship to something else that it reacts with, interacts with. So chemical and physical properties. In chapter 7, we'll finally get to this, the energy associated with these changes, the capacity to do work or to accomplish some change. So some quick definitions. Matter, anything that has mass and volume. Everything the universe is made out of is matter. And actually, everything the universe is made out of is represented by these, up to here, uranium. These 92 elements are the 92 elements in the universe. Everything you see around you is one or more of these things. One or either the element all by itself, or the element combined with another element, or to make a compound, or compounds mixed together to make mixtures of things. So these 92 elements are the fundamental building blocks of everything that is matter around you. Not everything is matter. The light coming from that light up there is pure energy. The light, there's no mass to it. It's electromagnetic radiation. It's it's energy being emitted as visible light. So not everything is matter. There's energy, and there's a relationship between those two things. But all the stuff that you can feel, see, breathe, the air, whatever, this is the matter that makes up things. Most things are combined with something. They're very rare that you are looking at an element. Here is one right here, aluminum. That's elemental aluminum. The air you're breathing is a mixture of two elements, oxygen and nitrogen, in their elemental form. So water is not an element, it's a compound, hydrogen and oxygen. So matter, we've got composition, the types and amounts of simpler substances that make up matter. Properties, like I said, you could talk about physical and chemical properties. So boiling point, density of water, that's a physical property. Color, its melting point would all be physical properties. Chemical properties have to be described in relationship to the interaction with something else. Yeah, a property that is observed without changing the composition or identity of the substance. When water boils, it's H2O as a liquid. It's going to become H2O as a gas. Still H2O. It has the same composition it had in the liquid form. It's just now in the gaseous state. Chemical properties, you actually have a change in composition. A couple examples. Here's an icicle. We never see those in Texas, but an icicle melting, water dripping off of it. It's a physical change. But if you took water and ran a direct current through it, the electrolysis of water, you could break it back down into hydrogen and oxygen, and that is a change. That's a physical or a chemical change. You're changing the composition. You're breaking the compound back down into its elements, and that would be a chemical change. All right, some quick ways of dicing up this stuff. Matter can be categorized into pure substances and mixtures. Pure substances are either elements, like aluminum, that would be a pure substance, sodium, hydrogen, oxygen. If you had a tank of oxygen, you'd have elemental oxygen there, pure. Or a compound like salt in the salt shaker, or water, H2O. H2O is pure. It's a pure substance. It is a compound. Mixtures can be divided up into two categories: homogeneous and heterogeneous mixtures. The air in this room is so mixtures can be gases, liquids, or solids. You can have mixtures of any of those. So in the gaseous stage, the air in this room is a mixture. It's a homogeneous mixture of oxygen and nitrogen, predominantly. There's a little CO2. We're exhaling a little bit of CO2. There's a few trace other gases maybe floating around in the air, but it's predominantly oxygen and nitrogen, and the composition is uniform throughout this room. So it's a uniform. That's what we mean by this homogeneous. Has the same composition wherever you sample it. Valero sends out a tank truck of gasoline to go to one of its gas stations, and that tank that has all different kind of organic compounds in it: octane and pentane, hexane, heptane. It's all in that tank, but they are all soluble in one another. So as that truck's going down the road sloshing around, it gets to a uniform composition. You could sample that truck anywhere and tell how much octane is in that truck. All right? It's got a homogeneous composition. Right, John? You're shaking your head? Sound right? Okay? So it's got a homogeneous composition. There's a heterogeneous composition. That's Italian salad dressing. Oil and water. Heterogeneous. The vinegar and water go to the bottom, and the oil's floating on top. And if you usually shake that before you put it on your salad. Otherwise, you're going to get all oil or all vinegar. So, just some terms. Yeah, so water is a pure substance. Sugar and water, it will make a homogeneous mixture. The sugar will dissolve in there. At the seashore, you get a little bucket of water, and it's a mixture. It's not, stuff will fall to the bottom. You'll get some sand and dirt, and it's not real homogeneous. Okay, now let's go on to numbers. Measurements in chemistry. We need to talk about this because we'll be talking about numbers and where do we get some of the conclusions. A lot of conclusions, a lot of the things that have been determined have come from really fine, careful measurement and noticing changes in weights or volumes or pressures, whatever. So chemistry is really, depends on some careful measurement and handling of the numbers. So let's look at rounding real quickly. There are times, now we're not going to talk about significant figures just yet, but let's just say your calculator showed you this number and you really only wanted to report to three significant figures or one decimal place, and you got 24.34999999. What you're going to do here, so you're going to keep 3 digits. You're going to get rid of the rest. Well, this is the only one that you need to be concerned about, and you can ignore everything after it. Doesn't matter that the 4 has a whole bunch of 9s. If this number is less than 5, you're going to leave this number alone and round it off to 24.3. So if the number you're dropping is less than 5, the preceding number is not changed. Here's 24.35, 111111. Again, ignore all of these numbers and focus on that number. If the number you're dropping next to the one you're keeping is 5 or greater, round up. Okay? Round up. So you change the 3 to a 4. Half the time you're rounding up. Half the time you're leaving it alone. That's the way your bank handles your interest. It's the way they should be handling your interest. They calculate things and it comes out that your interest for that month is 24.397. They'll round that off. Comes out to 24.393. They should round that down, not round it down, but leave it the same. So half the time they don't charge you that 3/1000th of a dollar, and half the time they do round that 7/1000th of a dollar up to the next penny. This gives you a little idea about significant figures. The bank is rounding off to the nearest penny, right? Why? 1 cent is the smallest unit of U.S. currency, a penny. A bank can't give you less than a penny. All right? So anything less than a penny is insignificant. It's not a significant number. We really need to round off to the nearest penny. And that's why we do that. Because our smallest measurement is a penny, our smallest way of measuring. So you're going to see that. All right, so just refer back to this. This is how we round. And then why do we round? Start looking at this. Okay, significant figures. Here's a red object that we're measuring with 2 different rulers. This ruler is calibrated only to the nearest centimeter. All right, so you can take a look at this and know that it is greater than 5 centimeters long, but it's less than 6 centimeters long. Somewhere between 5 and 6. But you can even take a look, and your eyes are good enough to estimate that next digit. It's not 5.5 centimeters long. You'd say, well, I think it's about 0.4. It's about 4/10 of the way to the next unit. So that would be the right number to record, 5.4 centimeters. And that has 2 significant figures. 2 significant figures. We're not talking about decimal places. We'll define significant figures here in a minute. Now, if we measured this with a different ruler, a more accurate ruler that was actually calibrated to the tenths of a centimeter, we'd look at this and see if I can even make that bigger. Yeah. Focus in on this and you see that 5.1, 5.2, 5.3, it's more than 5.3, it's less than 5.4, and it's closer to the 4 than it is the 3. So I'm going to make a guess that it's not 5.35, it's not 5.39. Looks like it's just a hair above 5.35, 5.36. And 5.36 has 3 significant figures. Again, we're not talking about decimal places. 1, 2, 3 significant figures in there. All right, so significant figures have to do with how you got the number. What was the capability of the measuring instrument you used to get the number? That's what gives significance, not your calculator. You can take 2 divided by 17 and you get a number with all kinds of decimal places after it, and you think, wow, look how accurately my calculator did that. Your calculator is a number generator. It doesn't know what is the significance of all those decimal places. The calculator doesn't know. You need to figure out what is the 2 mean, how significant was the number 2, how significant was the number 17 that went into this calculation to decide what is the correct significant figures. All right, here's just another example, different scales, double pan balance. Here's a digital scale that's good to the 10th of a gram. And here is a analytical balance that's good to, we can't see that very well. Can't see it very well at all, but there's a number, and a decimal point, and then 4 more numbers. It's actually, that's a 2 there. So there's point, what is it, 7652. That is taking you out to 10,000th of a gram. That's the accuracy of that balance. It can measure out to the 10,000th of a gram. So you can get more significant figures with that one. If this is 35.7652 grams, 6 significant figures. That balance is more accurate device. All right, so what are significant figures? Information bearing digits or figures in a number are significant. The measuring device used determines the number of significant figures. The amount of uncertainty associated with a measurement is indicated by the number of digits or figures used to represent the information. Okay, here are the 6 rules. This would be maybe a good one for you to print out or have handy. The rules. And let's see, Vincente, maybe you can turn this off for a little bit. Thank you. All non-zero digits are significant. So the number 7.314 has 4 significant figures. Number 2, the number of significant digits is independent of the position of the decimal point. 73.14 has 4 significant digits. They're all non-zero digits. Now these are the 3, these last 4 are the ones that will give you the most problem because they have to do with how do I deal with a 0. Okay, this is pretty straightforward. If the 0 is in between 2 numbers that aren't zeros, they're significant. So 60.052, 5 significant digits. If the zeros are trailing zeros, after the decimal point, they are significant. So if your bank owes you, going to a Bible app, that was interesting. If the bank owes you $24.70, they're going to give you, that's 4 significant figures. After giving you 7 dimes, they're not going to give you any pennies, because that's what they owe you, $24.70. So that is a significant digit right there. Trailing zeros. Okay, trailing zeros are insignificant if there's no decimal place. If I ask one of you how much money you have and you say, oh, I got about $100. That only has one significant figure. I don't know whether you got $95 or $105. You might not know. You say, last time I checked, I think I got about $100. But someone else counts out 5 20s and says, I've got $100. That's how I would report that. They know exactly. If we're going to go to a restaurant and it's going to cost $95, I know we're not going to do dishes at the end of the dinner. Okay? So you put a decimal point in there to upgrade the significance of those numbers. And leading zeros are not significant. So this number has only 2 significant figures. Yeah, 100, this has only 1 significant figure because there's no decimal point. It has only 1. So the number 1,000 has only 1 significant figure. 10,000, 1,000,000. You say, how many people are in San Antonio? I think it's around 1,000,000. All right? But if you go to the census office and they say it's 1,000,003, they say there's 1,000,003 people here, all of a sudden, bam, you've got a number with 7 significant figures. Because all of those zeros are between non-zero digits. And they say, yeah, 3 people came yesterday. We got 1,000,003 people. Okay. That's pretty accurate. It's pretty accurate. Okay, go for it. Number 1, let's just get, I might start calling some names, but let's get some volunteers. How many significant figures? 4 or 2. What kind of zeros are these? Trailing zeros. Are trailing zeros significant? Yes. 4. This number, okay, forget that. This number. 4. The zeros are between non-zero digits. This number. 3. 1, 2, 3. There's a decimal point in here. Okay, this number. How many? 4. Wow, we got all kind of numbers. 2, 4. I don't hear 6. 2 or 4? 4. Okay, 4. These are leading zeros, so none of those are significant. Here's our first non-zero digit. That's between, so there's at least 3. And that's a trailing zero. So that's significant. 4. All right, good. Well, let's see here. We're going into scientific notation. I'm gonna skip over to slide 23 for a minute. Here's where you need to use this and apply this, and you will apply it the most frequently, will be in calculations where you're either multiplying or dividing. And this is the simplest one to learn. It's the one you're going to use the most, fortunately. What's the rule? If you start taking numbers into a calculation, you have to start thinking about, how do I report the answer? What is the level of accuracy with which I can represent the answer to this calculation? And basically, I mean, you know that a chain is as strong as its weakest link, right? You pull on a chain, and where is the chain going to break? It's going to break at its weakest link. So it could be 5,000 links long, but you tug on it and stretch on it, and the weakest link is going to break. Well, a number can be as significant as your least significant number. All right, just keep that in mind in multiplication and division. The least significant number determines the answer. So go ahead and do that. Well, let's just look at this for a second. How many significant figures does that have? 3. How many significant figures here? How many significant figures here? Now take out your calculators and calculate the answer to that. Do that calculation. Now we're not talking about units, we're just right now talking about how to handle the numbers. What to do with things numerically. All right, now do you get something like this? This is what I'm getting. 29.75937916. Is that what you got? Okay, good. I punched numbers in right. Okay, now that's what your calculator said, and I just want you to recognize that your calculator doesn't think through significant figures. We can't take these numbers with 3 and 4 significant figures and end up with an answer that now looks like it's accurate all the way out here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 significant figures. I could do that just by a calculation? No. No, we only knew this to that level of accuracy. So we can't know the answer beyond 3 digits, 3 significant figures. So now we need to round this number off. Okay, this is where significant figures and rounding meet. How do we round? What does that round off to? 29.8. Here's the 4th digit. We're going to get rid of all of this. We're going to look at this. It's 5 or greater. It is 5 or greater. So we have to round up three significant figures. Okay? So whether you're multiplying 2 numbers together or taking a number and dividing it by another number or multiplying 2 numbers and dividing by numbers, just hunt for the number, the weakest link in the whole calculation, the number with the least number of significant figures, and that's how many significant figures should be reported in your answer. It's multiplication and division. Okay, addition and subtraction is a little bit harder. or harder to understand, a little bit different. So just look at it. If I measured two things, I've got something that's 54.4 centimeters long. I got something else. So I've got an object over here. It's 54.4 centimeters long, and I put next to it this other object, and I've measured it. It's 2.02 centimeters long, and I want to know what is the total length of these two things. I'm adding them. What's the total length? I obviously know this one a little bit more accurately than this one. But keep in mind over here, that's a question mark. I don't know what that is. It's 54.4 somethings centimeters long, but I don't know what it is to the hundredth of a centimeter, only to the 10th. So I add it up. I'll add the two up, and now I'm going to round it off. I'm not going to ignore this number. 2 plus a question mark is at least 2. It's 2 and something more. I mean, if this was a 0, it is a 2. If this was a 1, I don't know it was a 1, that would be a 3. But so I add it up and I round it off to not the 3 significant figures. I'm rounding it off to the level of accuracy that all the numbers have. They're all accurate to a 1/10 of a centimeter. So that's where I'm cutting off the final answer to the 1/10 of a centimeter, because that's the only one. And so that's a 2. I'm going to leave it at 56.42. If I had this one, let me just, if it was 54.4 plus 2.07, I would add them up, and in this case I would round it off to 56. So this goes to 56.5 centimeters. Why? Well, this is a 7. It's more than halfway to the next 1/10 of a centimeter. So I don't ignore that number. I'm going to still cut it off here. I don't ignore that number. I'll round it off to 56.5 centimeters. Yeah.
If they both went to the hundredths place, then your answer would be the hundredth place.
Right.
So you kind of go to the least place value, that's what your answer is.
Yeah, if this had been 56.41 plus 2.02, then yeah, the answer now is going to be 56. How do I erase that? Oh, wow, that was great. Yeah. If they both have the hundredths, then fine. Keep them. That's no longer a question mark. You measured it. Okay, let's so understand significant figures, how to handle them in a multiplication and division problem, how to handle them in an addition and subtraction problem. And then let's go back here. What did I skip? I skipped scientific notation. Let's just get that under our belts. Do we need another break? We got another half hour here. Anybody need a break? Let's take a 3-minute break. 3-4 minute break, all right? And we'll do scientific notation, and then please try to introduce temperature before we leave today. Okay, let's go back quickly again. This is the third one, third kind of topic, scientific notation. Just how to express big numbers in a shorthand format 4,300 is the same as 4.3 times 1,000. 4.3 times 1,000 is 4,300. Well, what is 1,000? 1,000 is 10 times 10 times 10 is 1,000, or 10 cubed. So that's all we're doing here. We haven't changed this number. It is the same number written in a different form, a shorthand form. Now, you don't need to write every number in scientific notation. If it's just a small number, 521, might as well just write 521. But if it's 5,217,000,000, da 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 da, you got all kind of zeros after it. You can convert that number into scientific notation. Is that 5 billion? Or is that only millions? Thousands, millions, billions. Yeah, I got billions, right? So I'm going to move that decimal point. The decimal point, even though it's not written there, is in that position. So I'm going to move it 1, 2, 3, 4, 5, 6, 7, 8, 9 places. So I will keep all of these numbers. 5.217 times 10. What did I say? I'm moving it 9 places. Times 10 to the 9th. So if I take 5.217, multiply by 10, by 10, by 10, 9 times, I would get back to 5,217,000. Now, this is also true. If I only moved the decimal point right to here, it'd be the same as 52.17 times 10 to the 8th, but that's not where we stop. If you're taking a number and are going to express it in scientific notation, then this number should be between 1 and 10. All right, so move it all the way to here. I'll move it all the way to here. You'd say, well, isn't that equal? Yeah, that's equal, but why do we do that? Well, I don't know if I need to explain it, but this wouldn't be the correct answer to that. In scientific notation, that's correct. All right? 10 to the 9th. You want to move it all the way back. Because if you end up with if you end up with this number and you're multiplying it by another number, 2.3 times 10 cubed, you can look at that and you say, well, 2 times 5 is about 10. You already kind of know what that part of the answer is going to look like. 2 times 52 is about 100. Yeah, you could say the same thing if you were working with 52.17, but we always want to get our numbers down between 1 and 10. And you would have a number here, and it's going to be times. What do you do when you have those 10 to the 9th times 10 to the 3rd is what? You add them. It's going to be 10 to the 12th. So you're going to get a number of 10, 2.3 times 5.2 is going to be 10 or 11 times 10 to the 12th. And yeah, so where was I here? There we are. Okay. Just a few more examples of it. 5.34. There's no decimal point here, so that's not a significant zero. 5.34 times 10 cubed. These are not significant zeros. We're going to come back to here. 5.3 times 10 to the 7th. Scientific notation is helpful in two regards. One, it can shorten a very big, a long number or a very small number. We'll look at small numbers here in a second. But the other thing is that it can, let's say, you see all those zeros, they all look like they're not significant. But let's say I know from the data that I gathered that although this is 53 million, I know that it's 53 million and these are zeros. I don't know what these are. But in my measurements, I knew that this is a zero, that's a zero. In scientific notation, I could actually preserve the significance of these two zeros and wipe out the significance of those four zeros by writing it in scientific notation. This has four significant figures. This number only has two. Yeah, so let's say we're talking about the population of Texas, and I don't think it's quite 53 million, but it's like 35 million or so. But if we're talking about population of California or something, we know there are 53 million people there. We know there's no any 100,000 or 10,000, but we don't know down in here. It's just people moving in all different parts of the state. This is uncertain, but I do know the certainty about those. I can preserve that in scientific notation. Small numbers. We're moving the decimal point to the right 2 places. So I give it a negative exponent. 5.3 times 10 to the minus 2. If I had 0.53, that's going to be 5.3 times 10 to the negative 1. 10 to the negative 1 is the same as that. 1 over 10. That's 10 to the 1 in the denominator. You bring it to the numerator, it's 10 to the negative 1. So that's the same as 5.3 divided by 10 equals 0.53. All right, this is 10 to the negative 1. That's what this is. 1 over 10. 10 to the negative 2 is 1 over 100. 10 to the negative 3 is 1 over 1,000. That's what we're doing here. 0.053, it's 5.3 divided by 100, or times 10 to the negative 2. Let me put that one. 5.34 divided by 10 squared is 5.34 times 10. When you take this out of the denominator up into the numerator, you have to change the sign of the exponent. That's what you do. Looked at that. English metric conversions. Okay, this starts getting into dimensional analysis. What slide am I on here? 24. I'm going to get good at this. So we're going to bring this up to 24. I'm going to give you a problem right now. Here's the problem. Get your calculators. Calculate how many seconds there are in a week. How many seconds are in a week? Okay, I'm not interested in the answer as much as the process. You got a number, write down a number, but you got some conversion factors here. 1 week equals 7 days. I'm going to abbreviate. 1 day equals 24 hours. 1 hour equals 60 minutes. And 1 minute equals 60 seconds. Okay? So let's do this problem with dimensional analysis. How many seconds, this is what I'm trying to calculate, are in a week? This is what I'm given. I'm given a week. 1 week. And I want to know how many seconds that is. Well, I'm going to convert my week into days. And how am I going to do that? Well, I need to put week down here because I want week to cross out. So I have, there are 7 days in 1 week. And I've just converted week to days. If I did that calculation, I'd end up with 7. Yeah, there's 7 days in a week. So now I want to convert my days into hours. So I'm going to put my day down here in the denominator because I want that unit to cross out with days in the numerator. So I have, there are 24 hours in 1 day. Boom, boom. I've just converted my week into hours. Now I want to convert the hours into minutes. Oh. Let's see, how do I erase that? Ah, good. So I need to put hours down here. 1 hour is 60 minutes. And then I want to convert my minutes into seconds. All right, minutes cross out. Now, there's an equal sign here. The unit over here, the only unit left over here is this. And that is the unit that I want. That's what the question asked for. How many seconds are in 1 week? I want my answer in seconds. Now, you could see, I could have asked you, what's the answer to this question? You give me a number. I don't want a number yet. I want to know that we're doing it properly. Dimensional analysis tells you you're doing it properly. If this unit came out in hours, I'm trying to calculate seconds, and I've got hours. Or I got seconds squared, or I got minutes per hour, or something like that. I don't have the right unit yet, so why pick up the calculator? Follow me? This is the way dosage calculations are done in the hospital. You analyze the units before you calculate the dose. The doctor says we need 50 milligrams per kilogram of body weight. Okay. What are you working with? A child. I'm in pediatrics. They weigh 25 kilograms. Okay, and what is the dose what is the concentration of this drug that has come up from the pharmacy? it's 8 milligrams per milliliter. Okay, you got all these units crashing in on you. And you got to figure out how much drug to give this child. You got to do the unit analysis, the dimensional analysis. Make sure you're doing the calculation correctly. All right, so this is dimensional analysis. What does that say? You analyze the units before you do the calculation. I want to encourage you to start writing down problems. Don't say, oh, the answer to this problem is this. Now, some of you that did that, you're going to get the right number here, but you've ignored the units. And what have you done in your head? You've said, I need to multiply by 60. I need to multiply by 60. I need to multiply by 24. If you did that, you were right, but you were, I won't say guessing, you were kind of following your intuition. You were taking a educated guess at it. Dimensional analysis proves to you that you need to multiply by 60. You follow me? Yes.
So for the week, so we wouldn't put seconds, like, slash week. If we did that would be wrong.
No, this is saying how many seconds are in a week. You would, what's the answer? What's our answer?
604,800 seconds.
That is the answer. That's the answer. Weeks have crossed out over here.
So we would have to cross, we can't put that in if we do that.
Yeah, I mean, is it that many seconds per week? Yes, that's true. But this is just saying how many seconds are in a week, and the answer is 604,800. Yeah, the week has gone away as a unit. That is how many seconds there are in a week, per week. But yeah, it would cross out. I'm trying to think of another example. Yeah, this would be the better way to answer it right here. Or times 10 to the what? All right? I don't know why it won't let me go back a slide. So that is a way to introduce a little bit this metric, this conversions. This is the way you're going to want to do conversions from English to metric. If we've got let's see, what unit do we want to use here? Yeah, if we've got 72 inches, how many centimeters? Here's our conversion factor right here. 1 inch equals 2.54 centimeters. Now the conversions factor itself does not tell you how to use it in your calculation. If I'm trying to convert inches into centimeters, what unit needs to go down here in the denominator? Inches. So 1 inch goes down there, and the 2.54 centimeters goes there. And so we get a number like what? What's the answer to that? What is it? Or to be consistent with our significant figures. This has 2, and this has 3. I would actually round that off to 180 centimeters. This has only 2 significant figures.
That was 0.88,
182.88?
Yes.
Oh, well, okay. Well, it's still going to be the same. Yeah, it's still going to be the same because that's the key number there. All right? That point's another point. Sometimes a student will take a number like 182, and I'll say, round it off to 2 significant figures, and they give me the number 18. No. Whenever you round off a number, you're getting a number that's approximately the number you started with. Approximately. Okay? So 18 is nowhere near 182. So 182 rounds off to 180. So yet you're not going to keep that 2 because that'd be a third significant figure, but we're going to throw a 0 in there just to hold its place. Follow me? So then let's take 976 centimeters, and I want to convert that into inches. So now what goes in the denominator? Centimeters. 2.54 centimeters goes down here. And actually, this number, keep in mind that it's not just 1 inch equals 2.54 centimeters. 1 inch, exactly 1 inch equals 2.54 centimeters. So that 1, that is not just one significant figure. Follow me? We're not saying approximately an inch is 2.54 centimeters. We're saying exactly an inch is 2.54 centimeters. So this has at least 3 significant figures in it. All right, so don't be fooled by a conversion factor and say, oh, like 1 hour is exactly 60 minutes. That's by definition. By definition. So we could say 1 hour with as many significant figures as you want is equal to exactly 60 seconds. That's not a rough idea. That's the definition of an hour. Follow me? Okay, so there's times when you have to, don't say, oh, I can only have one significant figure in this answer. This is, I kind of overlooked that right there. That thing has more than one significant figure to it. It's a conversion factor. All right, so this one, we're putting centimeter, just to prove the point, you take this conversion factor and you use it the way you need to use it. And dimensional analysis shows you. If I want to go from centimeters to inches, then I need to multiply by inches per centimeter. I get the centimeters down here so that they cross out. I mean, when they cross out, they become the number 1. This is why it's unit analysis. Anything divided by itself is 1. 2 divided by 2 isn't 0. 2 divided by 2 is 1. Okay. All right, so this will help you with some of these basic units of the metric system. The basic units for mass is a gram. For length, it's a meter. For volume, it is the liter. All right? The metric system is a 10-based system. It's based on the number 10. That's the beauty of the metric system. And you will have these prefixes. You have these prefixes that can be used, whether you're talking about grams, liters, or what's the other one? Meters. You got to think through it. you can use these prefixes in front of any one of those, and they mean the same thing. A milligram is 1/1000th of a gram. A milliliter is 1/1000th of a liter. And a millimeter is 1/1000th of a meter. So the prefix always means the same thing. And that's the beauty of it. So we're just working out, here's your basic unit, has no prefix, gram, meter, liter, has no prefix. It's just, that's the basic unit. But then you can go bigger to kilo, mega. Kilo is 1,000 grams. A kilogram is 1,000 grams. A milligram is a 1/1000th of a gram. So here you're going bigger, here you're going smaller. Nanotechnology has to do with really tiny particles. And you're going down to a millionth. Here's a thousandth, a millionth, a billionth. 1/10000000th of a gram would be a nanogram. Okay, I think we'll take it that far. Before Thursday, look for Chapter 1 homework. Oh, let me explain the homework and the reading a little bit. Reading. My expectation of you in doing these reading assignments is you may not read it for final total comprehension. Read it to be familiar with what's in that chapter, so that you know where to go when you walk away from here and say, boy, I didn't understand that. I better go read that section again. Or I think if I got a little bit more insight into that, I could get a grasp of it. You know where to get that. The homework assignments, you're going to get 2 attempts. All right? Your final grade will be the average of those 2 attempts. So don't just blow off the first attempt. You get a 95 the first time you do it, forget it. You're done with that homework assignment. All right? Don't worry about it. You get a 75, you say, I better do that homework again. And then if you get a 95, you'll get an 85 for the homework assignment. Follow me? Take those 2 scores, add them together, divide by 2, and that'll be your score on that homework. So, and then I think what I'm also going to do is there's a place where I can check, will you allow students to go back in here for study purposes? And I think I will allow that. What that means is, let's say you come up to exam 1 and you say, well, I want to do that homework again and see how well I would do. And it'll give you a fresh new homework, okay? You don't get the same questions every time you do these. It's pulling questions, it's changing numbers and all of that. So you say, well, I'm going to do chapter 1 homework again. It won't be for a grade, but it would be for further study, okay? So that's what you'll do. And chapter 1 homework will probably be due next Tuesday. But I'll try to open it up later this afternoon. So you could. Is it time? I don't know. Probably. It probably will say you got 2 hours to do it or something like that. It will have a due date, and when that due date comes, it closes. And after that, it'd be for study purposes only.
If you do it, will it tell you which, not necessarily the answer, but which questions were wrong?
I think so. Okay? Like I said, this is the first time I'm doing this, so there's a whole lot of things I can change and tweak and adjust, and probably sometimes I'll get them wrong, or it won't happen the way I want to do it. But I think that's what I'm going to do, is give you 2 attempts, average them, and allow you to go back in and do it again for study purposes. Okay? All right. See you Thursday.